Today we learned how to work with the inverse and identity matrices. So the first thing you're going to do is we'll find the inverse of a matrix, and then the second objective will be to determine if two matrices are inverses of each other. I went over the multiplicative identity property. It says that pretty much if you multiply anything by 1, you will get itself. So I said, what do we multiply by 5? So 5 times what will give us 5. Now that what has to be 1. 1 is what's known as the multiplicative identity. We have the same idea, and again you can reverse that order. We can take 1 times 5 and still get 5. So with this multiplication, this order does not matter. Okay, so we can take that idea and also apply it to matrices. We have what's called the identity matrix. It is a square matrix where the principal diagonal contains only ones and everything else is 0. So an example of an identity matrix, notice that we use I here to represent identity matrix. This is of a 2 by 2, and the principal diagonal values are 1, everything else is 0. I show you another example of a 3 by 3 where that principal diagonal is 1s and everything else are 0s. When you multiply by an identity matrix, it remains the same. So if I were to take a matrix, say it's 4, 1, 7, 8, and multiply it by the identity matrix, 1, 0, 0, 1, the outcome should still give us this matrix. Give it whatever we started with, that 4, 1, 7, 8. That's what this property shows. We can reverse the order and switch these and still come out with that original matrix. I know that in our previous assignments we stored in our calculator, we would store a matrix A as something and a matrix B as something, and we looked at, can we multiply A times B and get B times A? And we found out that that is not true, but it is true when we use the identity matrix. That order does not matter. To find an inverse of a 2 by 2, you will switch the values in the primary diagonal and change the signs. So if it's positive, it will become negative. If it's negative, it will become positive of all the values in the other diagonal. Then you have to multiply the inverse by the determinant of the original matrix. So I give you a formula. It looks like this. If A is our original matrix, then we're going to switch these places and change the signs of the other diagonal. So that is why these two end up switching places and these signs change. And then the last part of it says that you will multiply by the inverse of the determinant. Remember that this means that you'll be finding the determinant of matrix A, and we multiply it by the inverse, which is why we take 1 over that value. For example, if I found out that the determinant was 5, the inverse of 5 is 1 over 5. The inverse will not exist if the determinant is 0, and we talked about this because if we found out that the determinant was 0, then this fraction would become 1 over 0, and we cannot divide by 0. So in this first example, all we're doing is trying to find the inverse of this matrix. So to find the inverse of the matrix, the first thing that you're going to do is find the determinant of A, and to do that, remember that we multiply the values here. It gives us 12. Multiply the values of the other diagonal, which is 4, and we subtract them. And that will give us a value of 8. Now because that's not 0, we know that the inverse does exist. To find the inverse of the matrix, we take the inverse of the determinant, so 1 over 8, and then we take our original matrix and we change places of the primary diagonal. So this value becomes 4, this value becomes 3, and then we change the signs of the other values in the other diagonal. So they both become negative. And then the last step will be to actually distribute that 1/8 through. We talked about it as being a scalar, so it distributes to all 4 terms. So if we take 1/8 times 4, we get a half. 1/8 times -2 is -1/4. Same thing down here. And then 1/8 times 3 gives you 3/8. So we will practice this again. If you want to try it on your own and then check it when you're done, that might be a good idea. So we start out by finding the determinant of this matrix. We do that by multiplying our diagonal here, subtracting the other diagonal, which gives us 2. Then we take the inverse of the matrix. To do this, we start by taking the inverse of the determinant, so 1/2. We take our matrix and switch the values in the primary diagonal, change the signs in the other diagonal, and then your last step would be to distribute that through. Three halves, or you could write that 1.5. 1/2 times -2 gives you -1, -4 in the bottom corner, and then half of 6 is 3. Alright, we're also going to talk about what a multiplicative inverse is. If I have 5 and I want to multiply it by 1/5, I get 1. So we call this the inverse. We're multiplying together to get 1. This can also look like this. This says I can take 5 times 5 to the -1 and still get 1, or this represents the inverse of 5. Now if you remember your exponent rules that we learned last year, if this is a 1, or it is 1, if you multiply those, the bases stay the same, but we add those exponents. So you get 5 to the 1 plus a -1, which is 0. And 5 to 0, anything to a 0, is 1. And we have talked about this already in this class. So the inverse matrix is, you get an inverse when you multiply, if you multiply a matrix by its inverse, the result is the identity matrix. And notice once again that this order does not matter, that as long as we multiply an inverse by its matrix, we should be able to get the identity matrix. And we're going to use this idea to verify whether or not we have 2 matrices that are inverses of each other on the next example. So here it says, determine if the 2 matrices are inverses of each other. You're going to take the product, not produce, of the 2 matrices. So that means you're going to multiply these 2 matrices together. So I'm just going to say we're going to multiply these. And this is a good review for us, since we did multiplying of matrices before Christmas. So to multiply AB together, you're going to take the row by the column and multiply those values and then add them. So we take 2 times the 1/2, and then we're going to add the other 2 times -1. Now we're going to take that row by the second column, so this column, and you take 2 times 1/2 plus 2 times 1/4, and we'll do the bottom row. So we take the bottom row times the first column, you get -1 times 1/2 plus 4 times -1, and then we'll do the last one, where you take the row by the column, so -1 times 1/2 plus 4 times 1/4. And then all we do is find out what those values are. I'm kind of ran out of room there. So on the first one, when we multiply those, we get 1 plus a -2, which is -1. On the second value, we have 2 times 1/2 is 1, plus a 1/2 is 1.5. In the bottom left-hand corner, you get -1/2 minus 4 or plus a negative 4, so negative 4.5. And then over in the very last you have negative 1 times a half is negative 1/2 plus 1 is a half. Now if these were inverses of each other, then when we multiply them together we would get the identity matrix. Since we did not get this identity matrix, then we would say that they are not inverses of each other. So our answer to this question would be no, they are not inverses. Okay. Alright, that should get you through your assignment. There is one that I have you do in your calculator. If you will try it and follow the directions that I give you, then you should be just fine.